Welcome back. In the last couple of classes, we have been extensively discussing about multidimensional NMR spectroscopy with a special emphasis on two-dimensional NMR. I showed you a number of possible experiments possible with different acronyms like COSY, ROSY, NOSY, TOCSY, etc. Varieties of pulse sequences can be used. And I described about the advantages of this different 2D experiment, how the polarization transfer takes place between the interacting spins, all these sequences, and varieties of information was shared with you. And in the last class, exclusively, we discussed more about the COSY sequence, which is a two-pulse sequence, which is very important. So we even took some examples of the molecules and analyzed the spectrum. We found out also the diagonal B correspond to one-dimensional NMR spectrum. But there are coupled spins. There is a correlation between these two chemical shifts and gives rise to cross peaks in the COSY spectrum. So through which we are able to understand and I make the assignment of the coupled partners. That was a very easy thing. Okay, now we'll go further. And there are certain limitations for the COSY experiment. First, the polarization transfer between two spins is dependent on the scalar coupling. Sometimes it may so happen if the coupling is weak, you may not be able to transfer the magnetization, or if a long range coupling is there with coupling is of the order of negligibly small strength, you may not see the cross peak. So it depends upon the scalar coupling strength. And the 2D peaks have a fine structure in which multiple resonances contribute to diagonal or cross peak. We saw that. We saw autocorrelation peaks, and we also in the case of cross peaks also we saw multiplied factor. Fine structures will be seen. And another thing is for cross peak, this fine structure contains both positive and negative signal. That is a major drawback. When these frequencies are close by, it so happens if the coupling is very small, if these positive negative signal come close by, they may get completely nullified. They may finally, when they come so close, you may get zero signal. There may not be signal at all. And another thing is for broader peaks, these things will cancel out completely. Now, for a broader signal, these things will completely get nullified when they come close by. That's one thing. Another thing is the diagonals are always in phase. Gives us to strong diagonals. So as a consequence, if a small cross peaks close to larger diagonal peaks, often the what we call as the peaks which is extending on this called tails in the 2D spectrum, they obscure the diagonal peaks. Sometimes the diagonal peaks is so strong will obscure the cross peaks which are close to it. So we will not be able to see cross peaks very close to diagonal. These are all some limitations of the COSY experiment. So a number of variants of the COSY experiments have come out. I am not going to discuss everything because everything is an improved version. You can talk more about each and every pulse sequence. But remember, we have like sequences like 45, COSY 45, and we have what is called long range COSY, relay COSY, we have AE COSY, PE COSY, soft COSY, DKF COSY. There are a number of such variants, and everything is an improved version to address some of the challenges of the basic pulse sequence. So I will see at least one or two of these things, and what is commonly employed COSY sequence for the routine analysis. The commonly employed COSY sequence are, you can see COSY 45. This is an advantage. Intensity of the cross peaks nearby the diagonal becomes smaller and the diagonals become narrower. That's one advantage, one effect. And in this case, we have a tilt, cross peaks get tilted. As a consequence, depending upon the slope of the tilt, we can get signs of the coupling. This is one biggest advantage. It's like a small flip angle COSY or soft COSY. We can get relative signs of the coupling using COSY 45. Anyway, this is only an information. I will not go into the more details. And another thing is a long range COSY. The long range COSY is something, the additional fixed delay time is incorporated just before and just after the second antipulse. Then what happens? To allow the small spin-spin coupling to develop sufficiently and give detectable cross peaks. Small spin-spin coupling, if it is there, it will start evolving here, and you are going to get this evolution of such type of couplings, and you are going to get cross peaks, detectable cross peaks. And this is not very large value. It is of the order of 50 to 200 milliseconds you have to use. That's all. And of course, we can optimize for this particular things. You can take, if you want to get a long range, really long range coupling, if you know that value, you can say 0.5 by J is the what delta you have to use. And next point we have to discuss about the line shapes in 2D NMR. This is not only in COSY, in most of the 2D sequences. When the spectrum is recorded, if you look at, for example, this stack plot, you can see on either side, on the fore side, you will see a tile-like thing which is moving. Okay. This type of spectrum, when you take the contour, it looks like this. This is called a pure absorption line shape. Pure absorption line shape is always good for us. It gives you better resolution, and we have to get the spectrum, record the spectrum in pure absorption mode. There are various ways of recording the spectrum. Okay, in a magnitude mode, in pure absorption mode, pure dispersion mode, a variety of phase twisted line shape will be there in some cases. Varieties of phase line shapes will come. But always, depending on the pulse sequence, you may have a different shapes. Best is to use a sequence in such a way you get pure absorption line shape in the 2D spectrum. That gives a better resolution. And sometimes you get a peak like this, it like appears distorted like this. That is called pure dispersion line shape. And here you can see this, what is happening is this twisted line shape. Look at it. If you record the contour, it looks so bad. So there is a way to represent the 2D spectrum. Most of the time it is represented the absolute value mode. Phase sensitivity, generally phase sensitivity in absolute value mode. Absolute value mode means you discard the phase information. No, it is a magnitude mode. No phase information is available. But problem is, magnitude mode, if you record, it is not good for high resolution. Okay, it always produces line shape with both absorptive and dispersive shape. In the magnitude mode, when it so happens, it is broadening the signal and it is not suitable for high resolution. Phase sensitive data is better. It displays line shape in which an absorption dispersion modes are separated. So absorption mode is always preferred for a high resolution data, high resolution spectrum. Just to compare, look at the magnitude COSY spectrum. Look at it, it is like a star-shaped peaks are there. Both diagonal and cross peak appears as a star-shaped ridges are there in both dimensions. Both cross peak like diagonal peaks appear like this. The reason for it is, it has a mixed absorption dispersion line shapes. As a consequence, you see, when the peaks are too close, you will not be able to resolve. The magnitude COSY, that's why it gives sometimes broad peaks. You will not be able to get good resolution because it is a mixed phase. It has a mixture of absorption and dispersion lines. Of course, absorption and dispersion I already discussed with you long back when I discussed about the 1D. Okay. In reality, if I take Fourier transformation of double Fourier transform spectrum, any Fourier transformation has real part and imaginary part. This is very, very important thing to understand. It has a real part and imaginary part. In 2 dimensions, we have, again, in both the dimensions, we have real and imaginary parts. If you consider, there are 4 possible combinations. We can have imaginary in one and real in one dimension, imaginary, and real imaginary, and real. So, in the 4 quadrants, you can have different types of representation of the spectrum. And what is most important for us, you see, look at this one. Compared to this is really broad. Look at this one. This is having a tail line this end, and this is also having like this. Whereas this one is the best one. See, this phase in absorption mode line shape in both the dimension always gives you highest resolution. Please look at the spectrum, what is shown here. All you have to do is, you have to record the spectrum in double absorption line shape mode. Just remember this. There are various line shapes can be various types, but don't go for magnitude type spectrum. You always record the spectrum in double absorption mode. That gives you better spectrum in all the 2D experiments. You have to do that. And next is another thing what is called a DQF COSY. This is what is normally used, DQF COSY. Generally, it is better version of the regular COSY, what we use 1990 COSY. But only thing we have another flip small angle pulse with a delay between these two. Otherwise, everything remains same because it creates a multiple quantum, double quantum here, and we have to choose the double quantum pathway, and then it is selected through phase cycling. How do you choose the double quantum pathway? Pathway is because of phase cycling. I have not discussed about phase cycling and all those things till now. Of course, I gave you a big idea, a small idea, not big idea, small idea about phases of the pulses earlier. So, in fact, you can get the gradient version of this. We can select the double quantum pathway by using gradient. The gradient ratio, the small gradients are applied here and here. These are like spin-echo sequences in the middle of the delay here. So, when you select the ratio 1:2, you will select the double quantum excitation. And then we can get the spectrum of DQF COSY. Simply, I wanted to show you DQF COSY is a much better spectrum than COSY spectrum. Just please remember that. In a DQF COSY spectrum, if you take and look at the spectrum, fantastic spectrum. Look at this one compared to what you saw magnitude COSY spectrum and various types of spectra with the different line shapes you saw. In this case, both diagonal and cross peaks are anti-absorptive in both dimensions. It is called double absorptive mode. It's double absorptive, antiphase absorption is there, there is double absorption. Very good thing. It always gives us better resolution. In any case, always double absorptive mode spectrum, if you record, look at the resolution you get in both F1 and F2 dimension, it is double absorptive mode, and you will get beautiful, highly resolved spectrum. And even if you have a peak here near the diagonal, let us say, here or here, it is not going to be obscured like our magnitude type COSY. So you can, diagonal peaks will not the cross peaks which are close by to it. So the coupling can be measured with a better precision here in the DQF COSY. You get coupling information like this, very beautiful, you can measure it. So DQF COSY gives you the better spectrum. I gave you example of the COSY to analyze and everything. But what you should try to do is, you should always try to do DQF COSY spectrum. Don't try to do COSY, regular COSY. Another advantage, the single quantum like reference or solvent peaks, which use single peak, they all get suppressed. In the DQF COSY experiment, you don't get solvent peaks. Because a double quantum excitation, the single quantum peaks of solvents will not come through in the DQF pulse sequence. As a consequence, these solvents and reference signals, everything will be absent. We will get only well resolved double absorptive mode spectra of your samples. So that is the best thing you have to use. Just to compare regular COSY and then of this molecule at 1, 2, 3, 4, a pentapeptide. Regular COSY is this one, and this is the DQF COSY. Look at this one. Especially the diagonals, you see the ridges on either side. So this is if you have a spectrum like this, for example, you have a cross peak here. How do you identify? If this is a better, in case if there is, sometimes you get tiles on either side both. They're called, peak extends like this, the edges. They are called tiles. So T1 and T2 tiles will come sometimes so large, and these peaks get obscured. On the other hand, the DQF COSY, look at this one. Fantastic spectrum you are going to get. So always, whenever you want to do your COSY experiment for assignment purposes, do only DQF COSY. Don't try to do normal COSY. Okay. So now with this, there is lot more things we can discuss about COSY. Varieties of COSY sequences are there. How to get the sign of the COSY using AE COSY or PE COSY or soft COSY, we can discuss a lot. But that is pure for academic interest. Right now we will not go for that because you need to know how to analyze the spectrum of different molecules using various 2D sequences, and our time is also limited. So next I will go to what is called total correlated spectroscopy. It's a fantastic experiment, much better than the COSY. What is the advantage of this is, it establishes connectivity among all the coupled partners of a spin system. You know what is a spin system? I've already explained to you what is a spin system. The coupled partners of a spin system, if you take, let us say there are two different spin systems. You can identify the different spin systems easily. All spins which are coupled among themselves will be identified in one experiment. What you did in COSY, you went step by step. One is connected to two, two is connected to three, three is connected to four. Like a step by step manner, you went on identifying the cross peak for assignment purpose. But in TOCSY, one experiment, in one single experiment, you can identify all the coupled partners. It's a much, much better experiment. This is what happened. Exactly analogous to COSY. Only thing is, the magnetization transfer, instead of going to the immediate neighbor, it keeps on transferring from one spin to other spin among the coupled partners. So how much time it takes to transfer depends upon the time I am going to allow them to mix up. That is what the TOCSY is all about. So before that, let me tell you about a spin system. Of course, I discussed. Let me show you. Consider a molecule like this. Any set of protons in a chain of unbroken coupling interaction forms a spin system. In the 1D NMR when I was discussing, I told you about spin system. This is the exact definition of that. A chain of unbroken J coupling interaction, if it is there, that forms a spin system. Now here, look at it, this molecule. This, and this, there is a coupling. Let us assume 1, 2, 3, 4 bond coupling between this and this is 0. Similarly, 1, 2, 3, 4 bond coupling between this and this is 0. So then, among these spins, there is a coupling. Only thing is, there is no, CH3 is not coupled to these two. Let us assume that. Then, these three called three different spin systems. This forms one spin system because this is coupled to this, this is coupled to this, this is coupled to this. Similarly here, each spin is coupled among themselves. There is an unbroken chain of coupling. But this to this, long range coupling may be 0. No, doesn't matter. So long as there is a chain of unbroken coupling, that forms a spin system. So now we have three coupled spin systems. This is how you have to identify the spin system. And this TOCSY does in a one experiment. Very beautiful experiment. So TOCSY gives cross peaks among all the coupled partners of a spin system. How TOCSY works is a simple experiment. What did we do in the COSY? We had a 90 pulse here. Okay, T90, T1, 90 and then collected. But in this example, instead of a T1 pulse, we have what is called isotropic mixing. What we do isotropic mixing is, we bring the magnetization to x-axis. In that particular axis itself, you can apply a RF pulse for a longer duration. Then what is going to happen, we will retain the spin in that axis only for a long time. We are locking the spin in that axis. That is why it is called spin lock pulse. In the spin lock pulse, what happens is, it so happens it brings in a sort of what is called strong coupling effect among all the coupled spin system. What happens? It removes J coupling. Okay? When the J coupling completely removed, it becomes 0. Only chemical shift is there. What do you call that spin system? All chemical shifts are within a small range, that J couplings will be removed. Okay? Now, it forms a strongly coupled spin system, and then magnetization transfer among the spins become much better. So, what I was telling, what happens in the case of isotropic mixing is simply, you remember if you don't understand anything, it is called a spin lock pulse. You bring the magnetization from z-axis by applying a 90 pulse along particular axis, let us say x or y. In the same axis where the magnetization is there, we apply what is called isotropic mixing pulse, another RF pulse called a spin lock pulse, where the magnetization, the spin vectors are retained in the same axis for a long time. And it is all applied in such a way, the spins lose their identity. You cannot say, let us say in the spectrum, so many chemical shifts are there with so many spins, the different chemical shifts. That information is lost. Spins lose their identity and behaves like a strongly coupled system with the absence of chemical shift at all. There is no chemical shift at all. Then easy for the spins to talk to themselves and exchange magnetization among themselves. As a consequence, all the coupled spin system in a given system, all the couples magnetization transfer takes place. In the COSY, magnetized polarization transfer takes place only for first immediate neighbor and then second long range couple, third long range coupling like that. But in this case, because of the isotropy mixing, spins lose their unique identity and create a sort of, we are creating a strong coupling situation, and magnetization transfer takes place among all the coupled spin in an easy way. That's what happens. But in this case, how it happens? Let us see. We have different spin systems in the molecule. I showed an example where 3 different spin systems were there. Then how the magnetization is transferred? A beautiful example for this 4 into 100 meter relay. In one of the Olympics, what is happening? Look at it. There are 3 teams which are participating in this running relay. This is the Ghana team, USA team, and Italy team. What happens in the relay? The person who is going ahead first, and he has to transfer, pass on his baton to another person who is following him next. And he will run, and he will pass on the baton for another person who will follow him. The baton which they are carrying in their hand. So what they will do? This Ghana runner will pass on the baton only to his teammate, next person, and he will give to his next person. And he will not directly give to the last person. That's not allowed. He will give only to the next person. Exactly. The magnetization transfer goes from one spin to another spin very easily. First it goes to the immediate coupled neighbor, then the next one. Then magnetization transfer keeps on going. But between these teams, he cannot give his baton to this person. Not allowed, right? So this forms one coupled spin system, and this team forms one coupled spin system, and this forms another coupled spin system. So he will pass on baton to his team, he will pass on baton to his team. Exactly at this analogy, in a spin system, the magnetization transfer takes place among the coupled spin system, like the way it is going. First immediate coupled neighbor, then second neighbor, then third, like that. And depending upon the mixing time you are giving, in the pulse frequency, what I said, there was isotropic mixing time. Depending upon the mixing time you are giving, the extent of magnetization transfer takes place can be decided. You should not give too much also. Then there can be a back transfer of magnetization. Optimum you have to choose. Fine, doesn't matter. Now it happens. Let us now look at the spectra of 3 groups of 3 different spin systems which we saw. How does it look? These are the 3 spin systems we will take. There are 3 protons coupled here, 3 protons here, and 2 protons here. Hypothetical molecule. Don't worry about the chemistry, whether it is a CH3, CH2, we don't care. Whatever the terminal group may be, it has to be CH3, it could be CH2, we don't care. We are only hypothetically showing some molecule. This molecule, let us say A, gives us to a triplet, a quartet, and a doublet. Okay, this is what it is. One is a triplet, other is a quartet, last one is a doublet. Let us take B. B has only 2 types of protons. One is a doublet, other is a triplet. That's also fine. In principle, this has to be a quartet, that this should be a quartet, right? This has to be a CH3. So it has a, we are not worried about real chemistry. We are only a hypothetical molecule we are taking just to understand TOCSY. This is again 3 spins coupled. Now, again, let us assume one is triplet, doublet, doublet. Yeah, that's what we are going to get. Now, in reality, what is the type of spectra we are going to get? If I take 1D NMR, 1D NMR does not distinguish the spin systems. As far as 1D NMR is concerned, we are recording all the spectra of all the spin systems simultaneously, which are overlapped like this. It's a conventional 1D spectrum where you do not know which is the coupled spin system, which are the coupled partners also you do not know. But now, this is the spectrum, and we understood these are the different spin systems. Let us go and record the TOCSY experiment. Let us see what is going to happen. This is the beauty. Look at this one. Okay. Now in the TOCSY, this and this. See, this TOCSY, in this TOCSY experiment, doublet, and this triplet, they form a coupled spin system. See, now similar to COSY, sit on the diagonal, keep on going vertically completely to the end of the spectrum, same way from horizontally to the end of the spectrum. You see, you hit upon number of cross peaks. For this is the diagonal peak, this is coupled to this is also coupled to this. So these three group form a coupled spin system. That is exactly what we saw. In the previous example, when I showed this different color was given like that. But not only along this axis, it also gives along this axis. Similar to COSY experiment, TOCSY is also perfectly symmetric with respect to diagonal. Okay, so it is perfectly symmetric. You see, come along this axis, you see this peak, these two cross peaks. Go along this axis, you get two cross peaks. You can complete the square. You know which are the. In fact, you keep on giving vertical lines like this. You can identify all the three spin systems, all the three coupled spins like this. This one spin system with three spins, all can be identified. There is redundant information. One vertical row itself is enough to identify all the coupled partners. Okay, now go to the next one. Next one has triplet, quartet, and doublet. Okay, fantastic. You can see this. Now go along this axis. You can identify this group, and this group. All the coupled partners of this spin system is identified. That's also very easy. Now go to the next one. This one. We have a triplet and a doublet. Look, this is the triplet. Go along this axis. You are going to get you are going to hit a doublet. Similarly, there are only two peaks here. So this means this and this are the only coupled spins in this group. In this spin system, this and this are coupled partners. In this spin system, this and this are the coupled partners. So you can identify these from horizontal axis or the vertical. So in the F1 dimension also gives the similar information. F2 dimension also gives you similar information. So from TOCSY, in one experiment, you can immediately identify all the spin systems. I can give you one example where this type of application is seen, where it is you find it more useful. You go to analysis of a big peptide or a protein. It is made up of number of amino acids. Each amino acid, starting from the methyl group to the NH proton, if you go, they form a coupled spin system. What happens is, if you run a TOCSY and start drawing, lines like this, vertical lines. If there are 20 amino acids, you will get 20 vertical lines or horizontal lines like this. So you can identify each amino acid peaks from all the spin systems of each amino acid in a single TOCSY experiment. You understand? So the analysis becomes very simple by identification of spin systems of each amino acid. That is the beauty of TOCSY. So TOCSY is one of the important experiments where all the coupled spin systems can be identified by a single experiment. See these three. Now we'll compare what is a TOCSY and what is a COSY later. This is a TOCSY of one molecule called 3-heptanone. Okay, I think we tried to analyze this. I think, once we started analyzing 1, 2 in the COSY, and then we got the cross between 4, 5, 6, and 7, etc. Now, I know 1 and 2 are the coupled partners. I know 1 and 2 are the coupled partners. Start with 1, continue, completely come here. See, you can see only 2 spins coupled to it. 1, another. These are the only 2 spins which are coupled partner. It has to be 1 and 2. Whereas 7 is coupled to 6, 6 is coupled to 5, 5 is coupled to 4. Go sit at the diagonal of 7. Keep on coming down vertically. You can hit upon all the 3 cross peaks, which tells you this is coupled to this is coupled to this. See, all the coupled partners can be identified in one single experiment. You go like this or go like this. In either way, you are going to get all this identification of all the coupled partners. This is the best experiment. So, very easily, you can pick up the piece belonging to spin system. Okay, like this. This is one spin system. This is another. You can go, you take these peaks in the horizontal dimension, that is in the F2 axis, or in F1 dimension. Either way, this is in the F1 dimension, along F1 dimension, you can do, or you can do along F2 dimension. Both are same. Both will give you identical information. Okay. So two spin systems in this molecule were clearly identified. All the coupled partners for each spin system are identified in one simple experiment. Very single experiment. One experiment, everything can be done. Is the biggest advantage of TOCSY. Now we'll compare the same experiment, same molecule, TOCSY along with COSY. This is COSY. This is TOCSY. What is the difference between this and this? Remember, I said, in the case of COSY, first we identified molecule 1. From diagonal we came here, we went to horizontal again. No, here, number 1 we identified. From 1, diagonal we came here, we got a peak, went here, completed the square, and there was no other coupled partner. That was easy. When for these coupled protons, we started with 7, we came down, completed the square. From this diagonal, again we completed another square. From this diagonal, we completed another square, like that. We had to go step by step, okay, to identify all the peaks in COSY. Whereas in the case of TOCSY, it is different. In one shot, in one experiment, all the coupled partners have been identified. This is the biggest advantage of TOCSY. So, you people have got some idea. In the continuing with the COSY experiment, I told you this time today about some of the limitations of the COSY. And for overcoming that and improving that, many challenges have been addressed by improving this sequence. There are a number of variants of COSY experiments are there, like COSY 45, long range COSY, AE COSY, PE COSY, soft COSY, DQF COSY, varieties of things. But remember, I always tell you, you have to record DQF COSY if you are doing COSY, because that gives you double absorptive spectrum, very beautiful spectrum we saw, where resolution is much better compared to the normal COSY experiment. So the peaks near diagonal are not suppressed. So that's the advantage. It will not obscure, diagonal peaks will not obscure the cross peak near it. And extension of that, we went, this is called a relay COSY, multiple relay, one single relay, double relay, third relay, and finally all relay magnetization of all the coupled partners, it is called total correlation spectroscopy. So we show that total TOCSY is much better version, better experiment than COSY, where you can make the assignment of all the coupled partners in one experiment. So I have discussed about two types of correlation experiments, homonuclear. Now we'll go to heteronuclear correlation experiments, and then take one or two example of the inverse detection, and also J-resolved experiment, homo and heteronuclear. I will give some example, and then we will switch over to different topic. So I will stop for the day.